All right, folks, let's get started. So welcome back to the Sedona Community Office Hour. And today's office hour is for November. And let's get started. So first, I'm gonna go through the current status of Apache Sedona and also give a brief introduction of Sedona. And then we're gonna talk about the next release, which is 1.7. So first of all, I believe you guys okay, so Matthias, you're raising your hand. All right, so let's move on. So first of all, so if you guys heard of Sedona before, Sedona is an open source cluster computing engine for processing big geospatial data. And we have Sedona GitHub account. It is under the Apache Software Foundation. We also have a Twitter account and the LinkedIn account. So if you want to know the latest news, please follow us on LinkedIn and Twitter. And our website is at sedona.apache.org. So the website has much more content and also lots of tutorials. Okay. So the status of Sedona. As you see, there are many companies are using Sedona. So there are many logos listed on the right-hand side. I'm not going to repeat the names, but Sedona is being used by many companies in production. Sedona is a project we started in 2015, and it joined the Apache Software Foundation in 2020, and started in 2017. So it started to get lots of traction. And on GitHub, right now it has over 120 contributors, and it has 2,000 stars on GitHub. And the last month, it has over 2 million downloads. So that's a lot. And overall, Sedona's downloads have exceeded 38 millions. And this places Sedona among the top 0.3% most downloaded package on PyPy. So it is a very popular software. And here is a overview about Sedona architecture. As you can see here, so Sedona has multiple layers. So from the top, it has the spatial query processing layer. So this layer can actually work with a number of developer tools like Apache Zeppelin, Tableau, Jupyter Notebook, as well as GeoPandas. So the spatial query processing layer also provides a number of different APIs. In particular, it has Spatial SQL API, Scala Java API, as well as Python and R binding. So this layer equips with a number of distributed query algorithms. So it can take your spatial SQL query workload, and based on the size of the input, it will automatically determine how to distribute the workload among machines in this cluster. It also has the spatial query optimizer, which can actually collect statistics from your input geospatial datasets and determine which query algorithm is the best one for this particular input dataset. And the second layer is the distributed spatial dataset layer. So it has a spatial partitioning, spatial indexing, and the spatial serialization and deserialization. And it also works with different data structures, data models like batch processing as well as streaming data processing. And at the bottom, Sedona can actually work on top of different query engine. So it can work on top of Spark for batch data processing and on top of Flink for stream data processing. It also works on top of Snowflake. So there is a Sedona plugin for Snowflake called Sedona Snow, which is available on Snowflake Marketplace. So among the supported engines, by far our support on Apache Spark is the most comprehensive one. And in terms of data format, Sedona also support a number of different data formats for spatial data. like GeoJSON WKB, GeoParquet, as well as several raster data sources, including GeoTIFF and NetCDF and HDF. Sedona Docker image. So the easiest way to get started with Sedona is through the Docker image. So on Docker Hub, we have an official Sedona account and the Apache organization. So you can actually pull the image like this, use this command, docker pull Apache Sedona, and you can easily start a Jupyter Notebook interface from this Docker image, and you can play around with it, use the Python code as well as Spatial SQL code. Sedona follows the 3 month cadence to release the binary releases. So this year we have made a couple release. So the most recent one is Sedona 1.6 and 1.6 and 161. So 160 was released in May, and 161 released 3 months ago in August. And this month, within a few weeks, we are looking to release a new version, 170. So this is going to be a major release. That means it will include lots of new features and possibly breaking changes. So this is the about the 1.3 release. Now let's see. So what are the new features we're going to include in the 170 release? So there are three main things we're going to include. So first of all, the key nearest neighbor join. So key nearest neighbor join is one of the most important join operators that can enable users to find nearest neighbor for each object in a big data set. And today we have a community member, Feng Zhang, who is joining the call and will give us a presentation about what KNN Join is and how he implements this algorithm in Apache Sedona. So I will finish introduction about 2 other items, then give time to Feng to talk about the KNN Join algorithm. And this, by the way, this is probably in the past we have 2 spatial join operators in Apache Sedona. One is the range join, another one is the distance join. This is the third new join operator we have introduced recently. Another new feature we're introducing in Sedona 170 is GeoStats. So GeoStats is a toolbox we developed for scalable spatial statistic analysis. And the third feature is several DataFrame-based data readers. So let's take a look at the GeoStats. In the first release of the GeoStats toolbox, we actually include three new functions. So the first statistic functions we have is the dbScan clustering. So I believe many of you have heard of this. So dbScan clustering is basically try to cluster spatial data sets, spatial points, spatial objects based on spatial proximity. So you can actually easily run this query in Sedona use the Python API, Python and Scala API. So as you can see here, so you first create a data frame, and you send this input data frame to this dbScan function call. Eventually, it will show you the this output. So essentially, for each input geometry in this data frame, it assign cluster ID to this geometry. You can actually visualize the result on a map. As you can see here, so this is a dbScan result of a spatial data set. Tries to cluster them based on their proximity. As you can see here, you can easily get a bunch of clusters for the objects. So basically, nearby objects are put in the same cluster. All right. Second function in the GeoStats is hotspot analysis. So in the hotspot analysis function, we actually introduce a new index called getIsOrg. So basically, it tries to find the statistically significant hotspot for inside the spatial data sets. So in the past, you probably have been using spatial join, you probably using other using H3 or other kind of functions to do spatial aggregation. You aggregate spatial objects based on their H3 ID, based on their polygon census polygon shapes, right? So you get some sort of heat map, but this kind of result does not actually give you the statistically significant hotspot, meaning that so there will be probably some outliers, and you cannot 100% guarantee that so the hot region you see on this map is actually the hot region, and it is not affected by the nearby objects and not affected by some sort of randomness factors. So our new hotspot analysis in GeoStats using GeoStats, which give you statistically significant hotspot, and it tells you that if the score you get for this object is high, it is definitely a hotspot, and it gets rid of eliminate the randomness factor. So the input is still it is a data frame, spatial data frame, and output is a bunch of is a GeoStats score for each individual object. So basically, it gives you something called G star score. So the higher the score is, the hotter the area is. So that is higher score meaning a hot area. All right. So this is the hotspot analysis. The third one is the local outlier factor, LOF. So as you can see from the name itself, the outlier factor is to find anonymous anomaly data points by measuring the local deviation of given data points with respect to its neighbors. So basically, you want to see if a point is outlier, right? It has significant different spatial observations compared to its neighbors. So it is also easy to call this function in Sedona. Create a spatial data frame first and send it to this Python function, local outlier factor. We also have Scala API and Java API for that. So the output of this function is still data frame. For each individual input geometry, you get a LOF score. So the higher the score is, meaning that it is more likely to be an outlier. So we can also visualize the result on a map. If you look at this map, there is a circle. There's a circle around each individual point. So the size, the radius of the circle is corresponding to the outlier factor score. As you see here, usually the data that are considered as outlier, usually they have much higher radius, and those are the objects that are not within a certain distance of the other spatial objects. So this is the local outlier factor. As you see here, so the interface we have shown so far for the geostatistic toolbox are in Python and Scala as well as Java. So we are also working on a SQL interface for these functions, and it will be released very soon. I believe not in this 170 release, but it is very likely to be released in 171. Cool. The third feature, DataFrame-based readers. In this release, we are introducing two very cool DataFrame-based readers, one for the shapefile reader. So if in the past you use the shapefile reader in Sedona, so you probably already noticed that so it is a reader that is built on top of the RDD API. So there are a couple of drawbacks for this RDD-based data frame shapefile reader. So the most important problem is it does not preserve the data type. So essentially, all the columns when you read from this shapefile are considered as string value. So you basically lose the original data type. Secondly, so it does not work with, it has lots of problems when deal with nested folders, when it deal with multiple shapefiles within the same folders, it is quite hard to get it right. So in this new shapefile reader, so we are introducing this new data source actually called shapefile. You can easily call the function like this: Sedona.read.format. You provide this data source name, shapefile. It will be able to read different shapefile, and also even if the shapefile in different folders and shapefile are in very different formats, so it will be able to read them back. So the second one is the geo package reader. So it also a different based. So it allows you to read any kind of geo package. Basically, in particular, if you have lots of geo packages stay in the same folder, it will be able to read all that. You can use a data source named geo package to read this geo packages. And it has a couple options. For example, you can use the show metadata one. It will tell you actually the metadata of the geo package. As geo package is a standalone database file, you probably want to know the metadata and decide which part of the database file you want to load. And you can also specify a particular table you want to read from this geo package, right? By giving the option table name. Cool. This is the new features we'd like to introduce. And now I'm gonna hand over the presentation to Feng, and Feng will talk about the details of the K-nearest neighbor join. Feng, please feel free to share your screen and open your mic.
Yeah. Can anybody hear me?
Yes.
Okay, cool. All right. So, hi everybody. My name is Feng Zhang. I'm the principal software engineer at We Are Robots. So my work focuses a lot on building geospatial query engine on Apache Sedona and also on We Are Robots platform. So today I'm going to talk about a new feature that we introduced into the new Apache Sedona release, which is the distributed k-nearest neighbor join. I think I only have 2 minutes, so I'm not going to spend a lot of time dive into the details of the algorithm, but I will show how we apply our new algorithm to Apache Sedona platform. So just very brief what we have included in the new release 1.7.0. So we have a new KNN Join SQL syntax, which you can see on the bottom of the screen. Very easy. You have a new operator ST KNN, and then you have a few parameters there. So basically, you are trying to query for each geometry in the queries table, which is right here, to those geometries on the objects table, and try to find the k nearest the neighbors for each point on the query side. And if you want to use a planar coordinate, you set that to false. If you want to use a spherical coordinate system, you set that to true. So 4 parameters, very easy to use. And then all the others are the same. I mean, you can use any regular join syntax on your select statement, join statement, and you can also have a filter, the where class on the SQL as well. So pretty standard extension to our current Sedona SQL spatial SQL syntax. And also this is also available on the DataFrame API. So basically you can do df.knn join on the DataFrame that you load into the Python or Scala syntax as well. And when we do this, we basically introduce a new quadtree-based partitioner. This is specifically designed for KNN, but in the future, this may also be available for other type of join or any other feature as well. But right now, we have a new quadtree-based partitioner for KNN. And also we have a few tuning parameters for KNN Join as well, which I will talk a little bit later on this slide. So how do we actually implement this? So I want to talk a little bit about, the difference between KNN search and KNN join, because there may be some confusion, because Apache Sedona already support KNN search, right? If you go to our help documentation, it tells you can use a DF API to do KNN search, and also it provides some SQL syntax that's basically you can use a range join. And then by limiting the number of rows on that syntax to can search for a certain geometry. So the basic idea for KNN search is basically you give one geometry and then you find the nearest neighbors for that. So it's pretty straightforward. But a lot of cases, like people want to say, if I have a lot of geometries on a data set already, how can I find for each of them the nearest neighbors? So that's kind of like the difference between the KNN join and the KNN search. It sounds like very easy, but if you think about, if you have millions or billions point on your query side, this is actually not very easy because you need a very scalable approach. You cannot just iterate each geometry on your query side. So it's not going to be very efficient, and it will take forever to do that if you do it that way. So usually when people do KNN search, so the easiest way is just do the brute force, right? You can just calculate the distance between your query point to all the points in your objects data set, and then just rank them, and then find the k, the top case, and export from there. So that's easy to think, but it's very time consuming. It's not efficient. And then in our previous Sedona release, we have this R3 index, which can very efficiently find the KNN for an endpoint. But the cost is you need to build this R3 before you actually issue the query in there. So it's like two different ways that we support for the search. For the KNN join, I think we can do both. Which basically there's nothing prevent you to do like brute force join that way, right? But our approach need to be scalable. So I'm going to talk about how do we do that. An easy way to think about this, like, can we if the join is not efficiently on a global scale, how can we partition our object data sets, those geometry into different partitions, right? You can see here we have 1, 2, 3, 4 different rectangles that you can put each point onto these regions, and then you just broadcast the red point onto each partition, and then do a local join for each partition, and then get a global rank in your reduce. Your reducers, right? So that's a way to think. If your query size is very small, right? If you just have like 10 query points or 100 or even bigger. So if you can broadcast your query points to the partitions on the object side, then you can definitely do that, right? That's also a approach that we adopt in this release for that. But the problem is when you have a lot more query point or query geometries on the left side, there's no way you can broadcast them into each of the partition, right? Because you basically will overload your executors by doing this. So we have to send those red geometries into selected partitions instead of all the partitions, right? So that's, for example, you can see right now, for this point, probably you won't include the partition one because it's so far away. You already have enough point for your k nearest point, right? So basically so our implementation is find a way so that so I mean basically the trick is find the partitions that you should the minimal partitions that you should include for each point in your query side so that you have exact and enough geometries on object side that you can finish your can join. Like for example, in point you can see these red rectangles. They are so if you have any point in the region 3, in the partition 3, we guarantee the k nearest neighbors will be in this rectangle box 4, 3, 24, and 23. If we have the ability to do that, then it will reduce the number of computations at the number of points you will place into the partitions very much, right? So we do this by sampling. Basically, we sample the big tables on the object size, and then using those samples and a spatial algorithm to do this. So this diagram is basically show how can we calculate this. So basically, you pick the geometry. I mean, you pick one partitions on the object side, and then you use this equation to calculate a circle, and then you intersect this circle with the rest of the partition grid, and then you include all these partitions into the one that I talked about here, right? So this is how we optimize that. So let me quickly show like how actually it works. So basically, I have this notebook. I believe that this is already in our GitHub repository. So if you have access, you can go there to get the same notebook that you can try. Very easy. Just initialize your Sedona session, and then so for this example, I'm going to join a weather event. I'm going to KNN join a weather events dataset into a flight event. So basically, for each of the weather event or weather station, that you will find the k nearest flights around that at a certain point of time. Because it's a demo, so I'm going to limit our search into a certain boundary. In this case, it's a Wyoming state boundary. So basically, when you load the data, you add a filter, filter those points. I mean, the weather event point and 5 points within this boundary using a spatial filter right here. So now I have the query table, and I have the object table, and then this SQL basically will use the STKN syntax to join by finding the 4 nearest neighbors. Right? So you can do a random. It give you how long it will take. You can change like to 8, very easy. And you can maybe 16. I mean, whatever neighbors you want to find. And then the result will be in this one. The DF can join. You can cache it. You can count it. You can create a temporary view for that data frame, and then just do whatever you want on the following one. So here I will just select a few points and then put them in a map, which you can show here. Basically, you can see for each of the weather station, it will find the 8 nearest flights around it, and then because I have the string line, so you can see they're also shown the same map. Yeah, I mean, pretty easy to follow. The only trick is here you have a new STKN with your join statement. Everything else will be the same. So we have the documentation. If you go to the latest snapshot, so there's a new page called the nearest neighbor search. it will give you more information for each of the parameters and some of the like parameter you can use to tune it. Like for example, sometimes you have the tiebreakers. Like, do you want to include them or not? If yes, then you will get more than. I mean, there's a chance you can get more than k neighbors return because some of them are tiebreakers, right? And also you talk about if you apply the filter push down, what happens? So there's some discussion, this discussion point you need to be careful on that, and then it will give you some example at the end. What else? Yeah, I think this is pretty much. I think the new features are very easy to understand, but when you run it, you may have some performance issues. I mean, I encourage everybody to log an issue in there so we can fix that if that's real bug or a lot of people request that. Yeah, I think that's it. Yeah, back to you.
Cool. Thank you, Feng, for the great presentation. So let me share my screen. So that's pretty much the content about today's office hour. And at the end of this office hour, I'd like to still call for help for the Sedona community. So there are a couple different ways to contribute back to the Sedona community. Many people think, okay, so I don't know how to write very complicated code and how can we contribute back to Sedona. In fact, what we really need is not just about the core code. We also need lots of help with regard to the notebook examples, with regard to the documentation, website, tutorials, as well as release tests, right? So all these things are things that you can help. And for example, for the release test, so actually before we actually announce the official release of Sedona, we always first announce the release candidate on Sedona mailing list. So like release candidate 1, release candidate 2, so on and so forth. And usually we have a couple candidates, we have a couple volunteers that actually help us to check the correctness of each release. So that will help us to detect any obvious mistakes before actually make the release to Maven and the pipeline. So if this is something that you can help, so please reach out to us and or create issues or make PR directly to Sedona GitHub repository. We would love to have your show up in the community. Cool. So yeah, that's the presentation I have for today. And now it is time for Q&A. So if you have any questions, please feel free to raise your hand and we'd love to answer that. And if no question, we're going to do a roundtable introduction. Cool. I saw a question in the chat regarding from Dewey regarding long lag distance. So Feng, do you want to take that?
So basically, we have some distant metrics that you can pick. Right now, we limit it only like if you want to do the distance calculation on a planar coordinate system or a spherical coordinate system, is consistent with how the PostGIS. In the future, we may be able to configure that, right? Yeah, if we really feel like there's more specialized distance
Yes.
measure. Yeah.
Yes, as Ben mentioned, so everybody is able to speak freely right now. So if you want to talk, please just open your mic.
I have one question. It's not related to the KNN, but I just want to know because this one, like say, if you have that long, it will be index. The index is a single value.
No, it is not a single value. So we have actually on each activator, so we have a R tree that is built on top of spatial coordinates to speed up the local nearest neighbor curve.
Yeah, this is based on R tree, but I just say that I want to know, like, say, if our object is that long, and maybe sometimes the object is a large polygon, and you convert this one to the index. Is that index for each of that, like say, that long, and also for the polygon, they have same size of the index?
Oh yeah, so for this implementation, for this KNN Join implementation, so we only support points. So meaning that if your input is a set of polygons, it will take the centroid. If I remember that correctly, we will take the centroid out of the polygon, and then it become a set of points. Then we do the nearest neighbor join based on that. So the index we talk about in the Sedona community is now this kind of H3 S2 index. So we mean the tree index structure, data structure that can speed up query processing, the tree-like index structure.
Yeah, I'm just curious that, when you save that for, say, if I give you one that long, and that long is there should be like leaves on the trees, So whether you say I just say how you link from I give you one that long, how you link to the trees. I just say whether you guys save another table, say this is our tree or quarter tree. So you give a number to point to that tree, or just save that tree to that particular that long.
So the tree index structure we build it on the fly. So that means it is a one-time data structure. It is transparent to the user. So we built it on the fly, and once the query is done, so the index is gone.
Which means that we cannot save that one at all.
You cannot save that at all. So the same happens to the spatial join, the other spatial join in Sedona as well.
So my question is, if I only have, like, say, I just supposedly, say point, so they convert to the index is very quick. But if I have a large polygon, so that will probably take time to convert that one to the index. If I have, like, say, 1 million of a polygon, that will take time to convert them to the index.
Yes. So basically, so in the KNN implementation, we have two different, I would say, indexing. One is the R tree. The R tree is built on locally. So this is after you partition the data. So if your partition is not so big, then it doesn't take a long time. The quarter tree is global. We use them to build the partitions, so it's not really matter much, like on the sample data. So yeah.
Yeah, but I'm just curious that, if you have like a few number of the polygon, that would be quick. But if you have a huge amount of the polygon, whether they have a take time to convert that one.
So first of all, it will take time to build index for sure, right? So even for polygon, even for points, if you have just a point, it will take time to create index. But when we create index, we're creating a distributed way. So like the index structure we have, it is on each executor. So that means the index creation happens in parallel for multiple executors. And so usually for this kind of spatial data structure, like R-tree we build on each local executor. So when we build the index, we actually take the bounding box of the input geometry. It is actually doesn't really matter if it is a complicated polygon with hundreds of coordinates or it is a simple point. We always take the envelope to build index structure. So basically, this kind of index search, if it is nearest neighbor-based index search, or a distance-based index search, it is always based on the rectangle. It follows this kind of steps called filter and refine. You first filter based on index using the rectangle bounding box, and then you do the refinement after the fact. So it will not affect much on the index creation time.
So you mean that it doesn't matter how many polygons, there will be same time almost?
Yeah.
Oh, cool. Another thing that, when you're using the R tree or quarter tree, so this is a small box. But if if I have one point, in the end, how I know the point is inside of the smallest of the box? Is I have others algorithm or you guys have to decide this point belong to this polygon or not?
So for nearest neighbor, so we have different we have different algorithm for that. So for the spatial join, the distance join and range join, we use different algorithm for that. For nearest neighbor join, like we mentioned, so like Feng mentioned, so we have two layer of partitioning. So the first layer is a quadtree partition globally. So that partition is very tricky because we actually need to build a buffer. Like we have two data sets, the k nearest neighbor object side and the target and the target side, the current point side. So we actually need to build a buffer around each input current point, and then we make sure the nearest neighbor, the k nearest neighbor, is always guaranteed to within this buffer area. And then we do the spatial partitioning within each partition. As I mentioned before, so we have local index on each executor that allows you to do. So you have a current point, you can check it against the archery index. So the archery index, is nothing new. It's something that has been there for decades. So archery index is by nature can support nearest neighbor query. So essentially, it has the idea that the archery is to cluster data based on spatial proximity. So you can actually follow the search path of the archery to check if one point is within a certain distance of the polygons, because we know the bounding box of the polygons. So I can share that. So this is a very complicated algorithm to check if a point has k nearest neighbor in an archery. But it is a well-established algorithm and has been there like probably two decades ago. I can share that paper with you if you're interested.
Okay, thank you.
Yeah, I think there's a few more. One is does cluster DB scan work with polygons or just point?
So the cluster DB scan work with polygons.
Cool. Another one I see is do you have a roadmap you can share of new features you will add to GeoStats in upcoming release? Do you have any plan to add new features for GeoStats?
Okay. So in the first release, as we mentioned, so we have 3 algorithms added. So in the future, we are looking to add a new algorithm for sure. So we don't have an exact roadmap, but that's a good idea that we can set up one. So essentially, so our goal for the GeoStats library is, so we want to basically pick the most popular algorithm in scikit-learn, as well as there are lots of interesting spatial statistic algorithm in this library called Spatial. So if I'm typing the name in the chat. So we are also like borrowing ideas from this library. So we pick the most popular algorithm from this libraries and try to implement this algorithm in the distributed system. So we are not like copying their code. We use their idea. Like we pick the most popular algorithm and try to re-implement all those in a distributed environment. And we also want to make sure the API looks similar and the behavior looks similar. Okay, so I saw there is another question. So is there possibility of integrating Sedona in geospatial libraries directly or need an API? So I'm not 100% sure about that question, but at the moment, Sedona work well with the entire ecosystem. For example, it can take a GeoPandas data frame as the input, and then once you finish spatial query in Sedona, it can actually return the Sedona data frame as a GeoPandas data frame. And you will, so our Python API also allows you to write UDF user-defined function using Shapely. So if you guys use Python a lot, you will know Shapely is a very popular library that can deal with geospatial data. You can write UDF using Shapely API. So the input of the UDF is in fact a Shapely object, Shapely geometry object. And you can also, for our raster functions, you can also write UDF. So the UDF is compatible with rasterio and NumPy, which means that so the input of the raster data frame UDF is a rasterio object, or it is a NumPy array. You can do lots of operations on top of that.
Sir, actually using this Apache Sedona, can we use for GMap? For example, if I'm getting a raster from GMap, can I use this Apache SQL for doing query on that?
Right now, if you're using, you mean Google Map? Google Earth Engine, right?
Yes, GMap.
Yeah. So right now, if you like, we cannot directly read from Google Earth Engine, but if you talk about GMap, so GMap is a visualization tool on top of Google Earth Engine, I guess, right?
Yes, sir. Python API. It's
Yeah, so we do not work with, because we do not work with Google Earth Engine data directly. So that means you cannot just use GMap on top of that. But Qiu Sheng, the author of GMap, has written another library called LeafMap, right? LeafMap can work with a bunch of other visualization tools. So LeafMap work with GeoPandas data frame, and Sedona also work with GeoPandas. You can use GeoPandas data frame as the glue to connect the visualization tool and Sedona. So that's how actually many of our users do. So we can actually connect Sedona data frame with Kepler.jl, with Deck.jl to do all these kind of visualizations. Okay. So time's up. I need to take this question from Dennis. So Dennis, I saw you raise your hand.
Oh yeah. I was just, I hope I don't know if this question is specific to Sedona or not, or geospatial tools in general, but I noticed that a lot of the analytics we would do are data sets from the Earth, of course, and I was wondering whether these systems, how easily they could be adapted to work on other planets and moons and stuff like that as people start doing more exploration.
Yeah, that's a very interesting question. So, in Sedona, we basically have two modes. So one mode is that so we can calculate distance based on the Euclidean distance in the Cartesian coordinate system, right? So for that, users, if they have spatial coordinates, they need to translate that to a corresponding meter-based coordinate reference system. So meaning that I'm not sure actually about the coordinate reference system on different planets like Moon and Mars. So if these planets have similar coordinate reference system, right? And there is a tool that you can do coordinate, you can transform the coordinates to meter-based reference system on this planet. You can still use Sedona to do that.
Thank you. That's very interesting.
Yep.
I'm interested in, you said earlier about needing volunteers to write some things. I'll reach out to someone. I think I have some interest in maybe some ability to help with that.
Yeah, that's going to be great. Thank you very much.
Okay, thanks. Bye. Thanks for putting on the office hours.
Thank you.
I actually do have a quick question. I picked up your sort of quick start guide with its Docker image there, and I was getting it going. I couldn't get the spatial join to finish. It wasn't like it's a spatial join that would take GeoPandas like 30 seconds or so. And is there like, do I need to I had a pretty small Docker image. Like, is that something that would cause it not to finish? Or like, is there something really obvious about building a spatial index or something that I have to be aware of in that case?
So it should be able to finish, but I guess probably there are some setting issues we can figure out. So
I know I'm giving you no specifics or whatever, but I'm wondering if this is a question that comes up often, and apparently maybe it's not. I can obviously
there are
dig deeper.
there are this kind of issues in particular when it comes to large data set, right? When data set is very large, so sometimes you need to hand tune a few parameters in Sedona to make sure, like you need to hand tune the index. You need to hand tune the index to make it run faster.
Fair enough. Yeah,
Like
it's like 500 megs on disk, so it's not tiny, but not huge either.
Yeah. So probably there are some other factors could affect the current performance.
Well,
So
I was wondering if
we
there's an
can-
easy the tuning the index is a good lead. I'm very new to Sedona.
And also tuning the partitions. Tuning the partition is also matters. Like choose number of partitions of the input data frame. So sometimes by default it does not have lots of partitions, like just a few partitions, which actually affect the current performance. Just like you probably want to repartition data set. All right, guys. If there is no other questions, so since time's up, so we're gonna end the office hour today. And thanks everyone for attending the office hour today. And as I said, we always need help, right? If you want to contribute back to community, please feel free to create an issue, raise questions, and also join our Discord channel, right? Talk to us. All right. Thank you guys, and looking forward to see you again in the future office hour. Bye, guys.
Thanks, bye.
Thank you. Bye.
Thanks. Bye.